So I've decided to start the class with some of the most fundamental chemical laws there are. That way we can kind of build from the ground up. So I want to start with the law of conservation of mass. This is something I think everyone knows innately, but sometimes they lose some of the intricacies associated with it. So, law of conservation of mass. Mass is neither created nor destroyed. You're going to see a lot of these textbook definitions, and I want to encourage you to always try to go beyond these textbook definitions because they don't give you much unless you are already adept in the field. So this might not tell you much other than, oh, there's something called mass. It's neither created nor destroyed, but you don't have an intuitive sense for what that really means. I think, or you might have an intuitive sense for this one, but like some of the ones down here, they won't mean much to you until you get kind of your hooks in it. So I want to give an example. So for conservation of mass, let's say we have a person that weighs 200 pounds and they eat some food. Let's say they eat 1 pound of food. Now I've got okay. Let's see, they eat 1 pound of food. You should be able to predict what this person's new weight will be. 201 pounds. Okay, that's conservation of mass at the most basic level. If you eat a pound of food, you're going to be a pound heavier, right? If you eat 2 pounds of food, you'll be 2 pounds heavier. Okay? Some of you might say, but I've eaten a pound of food before, my scale didn't weigh me a pound heavier. Well, that's the scale's fault. Okay? That means the scale is not well designed, but that's basic conservation of mass, right? If you hold a 45-pound plate in your hands, you now weigh 45 more pounds. Okay. While I think this example is obvious, sometimes it's not as obvious. So like, let's say this 201-pound person now doesn't eat for 3 weeks. Well, obviously they're going to lose some of their mass maybe within the next couple of days. The food that they ate is going to come off. Let's say half of that food exits the body as waste. You can imagine how that might happen. And then half of that food they didn't need, so they stored it as fat. So now they're 200.5 pounds. Okay? Sorry, I didn't mean to zoom out there. Let's assume now that they don't eat for 3 weeks past this. So they're not going to use the restroom anymore to eliminate mass in that way. So they're not eating anything after they've done this. So for 3 weeks, they don't eat. They come back and they're 190 pounds after 3 weeks. Where did that 10.5 pounds go? This person's probably not going to be very happy after not eating for 10 weeks, right? They're smaller. Not that much smaller, but smaller. Okay, where did that 10.5 pounds go? It doesn't just disappear, right? So where did it go? Well, it left their body as carbon dioxide. You're constantly breathing out carbon dioxide, right? If you're not eating food, then the only way for you to breathe out carbon dioxide is to use your own carbon sources. So this person is using its fat, which is carbon chains, as a source of carbon for energy, and they're breathing out carbon dioxide as a waste product. So that's what we say when we say conservation of mass. Okay? The mass is not destroyed. That 10.5 pounds is not gone from the universe. It's just in the atmosphere as carbon dioxide now. Okay. I've done some work here. Let me erase some of this so you guys get more out of watching the video. Okay. So the first concept I want to cover is the law of definite proportions. And this is that a given compound always contains exactly the same proportions of elements by mass. So here's a great example of a textbook definition not telling you much the first time you read it. Okay, so if we're going to understand this, we need to have an example, I think, to go with it. So what this is essentially saying, if we've got a compound, right, let's say water. I'm not going to say the formula for water, you probably know it. Let's say we have water. It's going to contain the exact same proportions of elements by mass. It just so happens that water is 8 parts. Some of you guys are already panicking because you heard me use the word 8 parts with water. 8 parts by mass oxygen to 1 part, and I need to make sure that this is really clear that I say 8 parts by mass. This is why you guys are having a little panic attack when I'm saying this. 8 parts by mass oxygen to 1 part, let me write it over here, 1 part by mass hydrogen. Okay, before you think that I didn't teach you anything last year because you're saying, wait, but water's H2O. You're right, it is H2O. Okay? The reason that this is true, the reason it's 1 part by mass hydrogen and 8 parts by mass oxygen is because hydrogen, there are 2 of them, and each one has an atomic weight of 1. So that's an atomic weight of 2 overall. Oxygen has an atomic weight of 16. Right? 16. So it's 8 parts by mass oxygen to every 1 part by mass hydrogen, right? 16 to 2 is 8 to 1. Okay. The law of multiple let me finish the law of definite proportions. So no matter what water you're looking at by mass, it will always be 8 parts oxygen to 1 part hydrogen by mass. Okay? That's the law of definite proportions. Multiple proportions. I think this one's an even worse culprit of definitions that don't mean anything at first glance. So, when 2 elements combine to form a series of compounds, the ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. That probably means nothing to most of you that just read that. I know it didn't to me when I first read it, when I was taking the same course you're taking. So, let's break this into smaller chunks and try to get an understanding for it. So let's say we've got 2 compounds, right? Dalton's considered 2 compounds here that consist of carbon and oxygen. Okay, and we're keeping the oxygen amount constant, 1 gram. Oh, sorry, I just said that backwards. We're keeping the carbon amount constant, 1 gram of carbon. Okay, but we've got 2 compounds, 2 different compounds that consist of only carbon and oxygen. Compound 1 has 1.33 grams of oxygen that combined with that 1 gram of carbon. Compound 2 has 2.66 grams of oxygen that combined with that 1 gram of carbon. Do you have any ideas for what these 2 compounds could be? You've probably seen that you probably saw me erase them already in the video, but this one is CO, or it's probably CO. This one would be CO2, right? The way I can tell is there's twice as much oxygen in compound 2 as there is in compound 1, right? And this makes sense. Carbon dioxide versus carbon monoxide. Okay, here's another example of the law of multiple proportions that I accidentally left the answer to instead of working out right away. But we've got mass of nitrogen that combines with 1 gram of oxygen. These compounds consist of only nitrogen and oxygen. Let me erase these arrows here because I recorded this video once but didn't like how it turned out. So compound A is 1.75 grams of nitrogen with 1 gram of oxygen. Compound B is 0.875 grams of nitrogen with 1 gram of oxygen. And compound C is 0.4375 grams of nitrogen for every 1 gram of oxygen. Okay. I left the explanation, I left the answer there, but I haven't explained how I drew this conclusion. Well, we know that compound A has 1.75 grams, which is twice as much as compound B. So there's going to be twice as much nitrogen to oxygen in that case. Here, compound B has twice as much nitrogen compound B has twice as much nitrogen to oxygen as compound C, right? And the answers here are a little subtle. I think compound A and B will make sense to you guys. There's twice as much nitrogen in compound A as in compound B. But compound B and C have the same amount of nitrogen, but notice this is when compared with 1 gram of oxygen. So if we had 1 gram of oxygen in compound B, it makes sense that we have 0.875 grams of nitrogen. Nitrogen's a little less heavy than oxygen, right? It's 14 grams per mole versus 16 grams per mole. So 0.875 versus 1 makes sense. Here, NO2, we've got 0.4375. So we've got half as much nitrogen to oxygen. Not half as much nitrogen in general. That's the same, but it's half as much nitrogen to oxygen. Okay? And the law of multiple proportions states that you'll always have, when comparing compounds that consist of the same element but different amounts, if you hold one of them constant, like I hold oxygen at 1 gram, you'll always have these small little whole number ratios that exist, right? 2 to 1 here, 2 to 1. This one's 4 to 1 down here, right? That's the law of multiple proportions. So A to B is 2 to 1, B to C 2 to 1, A to C 4 to 1. Okay, those are laws. So we've covered law of conservation of mass, law of definite proportions, law of multiple proportions, and all laws are things that we observe to happen. We observe the law of definite proportions to happen. Water is always 8 parts by mass oxygen to 1 part by mass hydrogen. We observe the law of multiple proportions to happen. You always get these little small whole number ratios when you don't vary one of the compound's mass. Okay? And law of conservation of mass, we always observe mass to, if it enters a system, we observe the mass of that system to go up. Right? The person is our system here. If you eat a pound of food, you're going to go up in mass by 1 pound. How did they lose this half a pound of food here? I think we said that person wasted that food. How would they waste it? Well, that would be going number 2, right? So that's conservation of mass. This little example hopefully clears any misconceptions you had up with that. And then, so these are all laws. Atomic theory is an explanation for these laws. So these things can be explained if atoms exist. So these little small whole ratios can exist or can be explained if we have atoms existing. So this is the postulates of atomic theory. I don't want to go over them because they've changed since his time. For instance, we know that atoms are not indestructible objects anymore, right? That is essentially, that was proven in World War II through the atomic bomb by splitting the atom. So it's not an indestructible object. But a lot of this stuff is still good to go over. So two big modifications. Subatomic particles have been discovered. You can probably name them. Proton, neutron, electron, and isotopes were discovered. So isotopes, remember, are elements that have differing numbers of neutrons. It causes you to have slightly heavier or slightly lighter elements. The protons have the same exact numbers. We're going to go over these more in the coming weeks. I just wanted to go over these fundamental laws of chemistry. So, like, where did the concept of the atom come from? Well, it came from a need to explain these laws. Okay? I'll see you in the next video.